Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Mars. Let's be honest. When you close your eyes and picture it, what do you see? You see the rust.
Right, the rust.
You see that endless oxidized orange dust. Just rocks that have been sitting there baking in radiation for 3 billion years. It is the definitive desert planet.
It is. I mean, in our collective imagination, and certainly in the images we get from the rovers, it's a place of absolute desiccation. It really makes the Sahara look like a rainforest.
Exactly. And the story we've been told, the story that is basically in all the textbooks, is that the water is gone. Or, well, if it's not gone, it's locked up in the attic in the basement.
At poles.
Right, at the poles.
That's the prevailing narrative. We know there is water ice at the poles. We can literally see the white caps. But for human exploration, for the dream of actually living there, the poles are, well, they're problematic.
Problematic is a very, very polite way of saying absolutely lethal, isn't it?
It really is.
But here is where it gets interesting for our deep dive today. What if that story is wrong? Or, not wrong exactly, but missing a massive chapter.
A huge chapter.
Right. What if there are gigantic reserves of water? We're talking massive, active glaciers, hiding in plain sight, right near the equator, exactly where we want to land. And the only reason we haven't seen them is because they are wearing a disguise.
It sounds like a conspiracy theory, doesn't it? But this is actually the central thesis of a fascinating new piece of research we are unpacking today.
Yeah, so today we are looking at a breakdown of a study published in the journal Icarus by M.A. DePablo and a team of researchers. And the specific article that caught our eye was from Universe Today, written by Andy Thomaswick, titled "Martian Volcanoes Could Be Hiding Massive Glaciers Under a Blanket of Ash."
And this research essentially proposes that we might be sitting on the resource jackpot of the solar system, but to find it, we have to stop looking at Mars like a dead rock and start understanding how volcanoes and ice interact in really specific ways.
And to do that, we have to start, of all places, in Antarctica.
We do. We have to look at a very specific, very strange island on Earth to decode what is happening on Mars.
So here is the mission for this deep dive. We're going to find out how a volcano in Antarctica is basically the decoder ring for Martian geology. We are going to look at the smoking guns that prove these glaciers exist. We'll explain why our billion-dollar radar satellites completely missed them. And then we're going to talk about the catch. The legal catch.
The incredible irony that finding this water might make it illegal to actually touch.
Right. So settle in. We are going really deep on this one.
Let's do it.
I want to start with the accessibility problem, because I feel like a lot of people listening might think, water is water. If we know there's ice at the Martian poles, why are we so obsessively hunting for it at the equator? Why can't we just land at the North Pole, melt some ice, and make a cup of tea?
It's a great question, and it really comes down to the sheer brutality of the Martian environment. You have to remember, Mars is already incredibly cold. The average global temperature is something like minus 80 degrees Fahrenheit, but the poles are a completely different beast.
How cold are we actually talking?
During the polar winter, you are looking at temperatures dropping to minus 195 degrees Fahrenheit.
Wow.
Yeah. That is cold enough to freeze carbon dioxide directly out of the atmosphere. That is actually why the caps grow and shrink. It's dry ice freezing and sublimating.
Right. So if I am trying to run a habitat or a rover or just keep my blood liquid,
you are fighting a losing battle. Materials become brittle, electronics fail, lubricants freeze solid, and then there is the darkness. The polar regions on ours, just like here on Earth, experience months of total darkness. If you are relying on solar power, which is our primary energy source for these missions, you are dead in the water.
So operationally speaking, the poles are a nightmare.
An absolute nightmare. But there is another layer to this, which is the regulatory hurdle.
The space lawyers.
The planetary protection officers, yes. We have an international agreement that we cannot contaminate what are called special regions on Mars. A special region is defined essentially as anywhere that Earth microbes might be able to survive and replicate.
And since life needs water.
Exactly. The poles have accessible water ice. If we crash a lander there, or if a human walks around there with a leaky spacesuit, we could introduce Earth bacteria into a water-rich environment. That could completely destroy our ability to ever detect native Martian life. We simply wouldn't know if the bugs we found were Martians or just hitchhikers from Florida.
So the poles are essentially the forbidden zone.
That's right. They are the most scientifically valuable spots, so we aren't allowed to touch them without extreme billion-dollar sterilization protocols that just aren't feasible for large-scale human missions yet.
Which brings us to the Holy Grail. We need water, but we need it where it's warm, where there is sunlight, and where the planetary protection rules are a little more relaxed. We need water at the equator.
Ideally, yes. The mid-latitudes or the equator. That is where you have the solar energy. That is where the thermal management of your base is easier. That is where you want to build.
But the equator is dry. It's a desert.
Well, that has been the assumption. We look at the equator and we see dust. We see rock. But for decades, geologists have been looking at satellite images of these regions, specifically around the volcanoes, and seeing things that look, well, wrong.
Wrong how? Like out of place.
Yeah, they see shapes, lobate shapes, these long tongues of material that look like they flowed down a hill. If you saw that exact shape on Earth, you would immediately say, that is a glacier. But on Mars, at the equator, exposed ice is impossible. It would sublimate, turn straight from a solid into a gas almost instantly in that thin atmosphere.
So scientists are looking at these shapes and saying, it looks like a glacier, but physics says it absolutely cannot be a glacier.
Exactly. And that cognitive dissonance is exactly what this new paper is trying to resolve. They are basically saying it is a glacier, it's just wearing a heavy coat.
And to prove that, they found a twin, a geological twin right here on Earth. Let's talk about Deception Island.
Ah, Deception Island. It is genuinely one of my favorite places on Earth, geologically speaking.
Even the name Deception Island, it sounds like a villain's lair from a spy movie.
It really does. It's actually located in the South Shetland Islands, just off the Antarctic Peninsula. And it's named that because from the outside, from the ocean, it looks like a solid, impregnable island. But it's actually a donut. It's a ring.
A caldera.
Right. It's the flooded caldera of an active volcano. You can actually sail a ship right through a narrow breach in the wall, a spot called Neptune's Bellows, and anchor inside the center of the volcano.
That sounds incredibly ominous.
Yeah.
Anchoring your ship inside an active volcano.
It is. And it's not just technically active. It is historically very recently active. This thing erupted multiple times in the late 1960s and 1970s. And those specific eruptions are the key to unlocking our Martian mystery.
Because Deception Island isn't just made of rock. It's rock and ice.
Exactly. It's heavily glaciated. So when those eruptions happened, specifically the big ones in 1969 and 1970, you had this violent, chaotic interaction between magma and ice.
Now, when I think of lava meeting ice, I think of melting. I think of massive steam clouds and catastrophic floods.
And that definitely does happen. But here is the nuance we need to look at. These were what we call free photomagmatic eruptions.
Freedomagmatic. Okay, that is a $5 word. Break that down for us.
Sure. It means the magma interacts directly with water, usually groundwater or glacial melt, and it basically explodes. The steam expansion pulverizes the magma into tiny microscopic fragments, ash, dust. So instead of just flowing rivers of lava, you get these massive, towering plumes of black ash raining down on everything for miles.
So it essentially rained black dust onto these pristine white glaciers.
Yes, it blanketed them completely. And here is where the physics gets incredibly cool. You would instinctively think hot ash falling on a glacier would melt the whole thing.
Sure. Hot rock, cold ice, melting ensues.
But ash is very porous. It is full of tiny air pockets. It's actually an incredible insulator. Think of it like a giant blanket of styrofoam. If you put a thin layer of hot ash on ice, sure, the top millimeter melts, but once that ash cools down, it forms a crust, a thermal barrier.
So it stops being a heat source and immediately starts being a protective blanket.
Exactly. It shields the ice from the sun. It shields it from the wind. It traps the cold in. So on Deception Island today, there are places where you can walk on what looks for all the world like a dirt hill. It's gray, it's rocky, it looks like solid ground. But if you were to dig down just a meter or so with a shovel, you would hit solid, ancient glacial ice.
A dirty glacier. Or a glacier in an Earth suit?
A debris-covered glacier. That is the technical term. And this gives us a very clear model, a mechanism. If it can happen so perfectly on Deception Island, could it happen on Mars?
So the researchers took this model volcano erupts, ash covers ice survives, and they looked at Mars. And they found a match.
They did. They turned their attention to a specific region called Hecates Tholus.
Hecates Tholus, another great name. Who is Hecate?
The Greek goddess of magic, crossroads, and ghosts. which is actually very fitting for a dead volcano.
Very fitting. So what exactly is Hecates Tholus?
It's an ancient shield volcano in the northern hemisphere of Mars. It's incredibly old. We are talking billions of years. But when the researchers looked at the flanks of this volcano, the long slopes leading down from the peak, they saw the exact same morphological features they saw on Deception Island.
Morphology meaning the physical shape and texture of the land.
Right. They didn't just see generic rocks or impact craters. They saw specific patterns that, on Earth, only ever form when you have a massive body of ice moving under a blanket of debris.
So the working hypothesis is this. Hecates Tholus erupted a long time ago. It spewed massive amounts of ash. That ash covered the glaciers that were sitting at its base. And now, millions or billions of years later, those exact same glaciers are still sitting there, perfectly preserved under a layer of rock and dust.
That is the theory. But in planetary science, you can't just look at a picture and say, well, it looks similar, so it must be the same thing. You need proof. You need evidence that creates a signature that only ice can create.
The smoking guns.
The smoking guns. And this paper identifies 3 very distinct ones.
Let's walk through these because this is the real detective work.
Oh.
Smoking gun number 1. Crevasses.
Crevasses. Now, most people kind of know what a crevasse is. If you've seen a documentary about climbers on Everest, it's the terrifying, seemingly bottomless crack in the ice.
Right. The abyss you don't want to fall into.
Exactly. But physically, why does a crevasse actually form? It forms because ice is a solid, but on a massive scale, it flows like a very, very slow, thick liquid. It is plastic. When that flowing ice goes over a bump in the bedrock beneath it or has to turn a corner, it stretches. And because the top layer of the ice is brittle, it snaps. It cracks.
Okay, so cracks mean movement.
Precisely. If you just have a pile of dirt, static dirt, it doesn't form systematic, deep, parallel cracks. It might slump a bit in a landslide, but it doesn't fracture in these very specific, predictable patterns.
And we see these exact cracks on Deception Island.
We do. We see them incredibly clearly in the high-resolution satellite imagery of the ash-covered glaciers there. And, crucially, we see these exact same fracture patterns on the slopes of Hecates Tholus.
So we are looking at a Martian surface that is broken in a way that suggests the material underneath it is stretching and flowing downhill.
Yes. It implies that the core of that dirt pile is actually something mobile, something that behaves exactly like ice.
Okay, that is compelling. But rock can crack, earthquakes happen. What makes it definite? That brings us to smoking gun number 2. And this is a word I had honestly never heard before reading this paper. The Bergschrund.
The Bergschrund. It's a wonderful German word. Berg meaning mountain, Schrund meaning cleft or fissure.
It sounds like a heavy metal band. We are the Bergschrund.
It really does. But geologically speaking, it is a very specific, very important feature. A Bergschrund is a special type of crevasse that forms at the very top of a glacier.
At the head.
Right. Imagine a massive glacier sitting in a mountain valley. The top edge of the ice is frozen solid to the mountain rock face. It's stuck there. But the rest of the massive body of the glacier is incredibly heavy, and gravity is constantly pulling it down the valley.
So it pulls apart.
It tears away. The moving ice physically rips away from the stagnant ice or the rock face. That tear creates a massive, deep, gaping crack right at the very top of the system. That is the Bergschrund.
It's the separation point. It's basically the ice saying, I'm leaving now.
Exactly. And here is the kicker for our Martian mystery. You do not get a Bergschrund in a landslide. You do not get it in a rockfall or a tectonic fault. You only get it when you have a cohesive, highly viscous mass that is slowly sliding downhill under its own immense weight.
And we found these specific formations on Mars.
We did. The team identified surface features at Hecates Tholus that matched the geometry of an Earth Bergschrund perfectly. And we aren't talking about small little cracks here. Some of these features are up to 600 meters long.
600 meters. It's like 6 football fields. That is huge.
It's massive. To have a continuous sweeping fracture that large implies an enormous body of material moving in absolute unison. It is a very strong indicator that we aren't just looking at loose dirt sliding down a hill. We are looking at a coherent sheet of ice that is, or at least was, slowly sliding down the volcano.
That is wild. So we have cracks showing flow, which are the crevasses, and cracks showing detachment, the Bergschrunds. What is the third smoking gun?
The third one is found at the other end of the glacier, the bottom. It's the bulldozer effect.
I like the sound of that. What is the bulldozer effect?
Geologists formally call them push moraines. Imagine a massive bulldozer driving through a field of loose soil and rocks. As it pushes forward, a huge pile of debris builds up right in front of the blade. Right. Now imagine the bulldozer just stops and backs up. That big ridge stays there.
It marks the furthest point the bulldozer ever reached.
Exactly. Glaciers are nature's bulldozers. As they slide down the valley, they push thousands of tons of rock and soil in front of them. When the glacier eventually retreats, or in this specific case, when the ice simply stops moving and stabilizes, it leaves behind these very specific bumpy, ridged terrains at the terminus.
And I'm guessing we see this at Deception Island.
We see it clearly. The ash-covered glaciers push the debris into these distinct lobes, and we see almost identical lobate ridges surrounding the base of the flows at Hecates Tholus.
So let's put the whole puzzle together here. We have the massive detachment tear at the top, the flow cracks in the middle, and the rubble pile pushed up at the bottom. It is the complete anatomy of the glacier.
It is. If it walks like a duck, quacks like a duck, and pushes rocks like a duck, it's probably a glacier.
And I have to play devil's advocate here, because there is a huge glaring difference between Antarctica and Mars.
The atmosphere.
The atmosphere. Mars is effectively a vacuum compared to Earth. The atmospheric pressure is tiny. If I took an ice cube right now and put it on the equator of Mars, it wouldn't melt into a nice little puddle. It would sublimate. It would turn straight into gas and just vanish into the thin air.
Correct. Exposed ice is fundamentally unstable at those Martian latitudes.
So if these glaciers really are millions of years old, why are they still there? Why haven't they just evaporated away over the eons? Even with a dirt blanket, surely the gas would eventually escape.
This is the survival mechanism question. And the authors of the paper propose a really elegant two-stage process to explain exactly how it survived.
Walk us through that.
Okay, stage one. The volcano erupts. The glacier is covered in ash, but as we discussed with the crevasses, the glacier is still moving. It cracks. It forms these deep fissures.
Which opens the ice underneath directly to the Martian air.
Right. And at that exact moment, sublimation does happen. The pristine ice exposed deep in those cracks instantly turns to gas and escapes. But then stage two kicks in.
The patch kit.
Exactly. Mars is an incredibly dusty place. We have global dust storms. We have more volcanic ash falling over time. That ambient dust settles right into those open cracks. It fills them up.
Like spackling a hole in drywall.
Perfect analogy. The dust fills the crevasses and creates a dense plug. And once that plug is formed, the system is sealed, the dust gets compacted, it becomes a physical barrier that water vapor just cannot easily pass through.
So the ice is basically trapped inside its own patched-up shell.
It's sealed in a geological time capsule. The authors argue that what we see today, these shallow, dusty troughs on the surface, are actually just the ghosts of the original crevasses. The ice deep below has retreated slightly, the dust has slumped in to fill the void, and now the whole system is in equilibrium. The sublimation has stopped completely because the seal is airtight, or, well, Mars-tight.
That is incredible. So the very environment that usually destroys the ice, the blowing dust and the dry conditions, actually helps seal it in and protect it.
Nature always finds a way.
Okay, so the geology makes sense, the physics of the preservation makes sense. But there is one giant billion-dollar technological elephant in the room, and we really have to address it.
SHARAD.
SHARAD, the shallow radar instrument on the Mars Reconnaissance Orbiter. This is a machine built specifically to find underground ice. It sends radar waves down, they bounce off the subsurface ice, and we get a nice picture. We have used it to map the poles. We have used it to find buried ice all over the planet.
It is arguably our primary tool for exactly this kind of work.
So did it beep. When SHARAD flew directly over Hecates Tholus, did it say, bing, giant glacier right here?
It did not.
It was completely silent.
Worse than silent, actually. It gave us noise, clutter. And for a long time, critics of the glacier theory have used that as definitive proof. They say, look, if there was a mile-thick glacier sitting right there, the radar would absolutely see it. It didn't see it, therefore it's just a pile of rock.
That sounds pretty logical on the surface.
It sounds logical, but it completely ignores the physical limitations of the technology itself. The paper argues that SHARAD is the right tool, but Hecates Tholus is the absolute wrong geometry for it.
Explain that. Why does the physical shape of the volcano matter to a radar beam?
Okay, let's do a little bit of physics. SHARAD works by sending a radio pulse straight down towards the planet. We call that nadir pointing. The pulse hits the surface and part of it bounces back. Part of it penetrates the ground, hits the denser layer of ice below, and bounces back.
And you measure the time difference between the two bounces to figure out exactly how thick the ice is.
Exactly. But this entire system relies on what we call specular reflection. Think of it like a mirror. If you stand directly over a mirror that is laying perfectly flat on the floor and you shine a flashlight straight down at it, the beam bounces straight back up into your eyes. You see the bright reflection.
Okay, makes sense.
Now imagine that same mirror is on a steep slope. Say it's tilted 20 degrees. You are still standing directly above it. You shine your flashlight straight down. Where does the beam go?
It bounces off at an angle. It hits the wall across the room. It definitely doesn't come back to my eyes.
Exactly. The receiver antenna on the satellite is your eyes. Because Hecates Tholus is a volcano, it inherently has steep, sloping flanks. The radar pulse hits that slope and scatters wildly away from the spacecraft. We just don't get a clean echo back.
So we aren't seeing no ice. We are just seeing a deflected signal.
We are seeing blindness. We are seeing clutter caused by the extreme roughness and the sharp angle of the terrain. The lack of a clear signal is not evidence of absence. It's simply evidence of a bad viewing angle.
So the most sophisticated scanning tool we have is essentially useless for this specific type of geological formation.
Until we can physically tilt the radar or get a completely different vantage point, yes, we are flying blind. Which brings us right back to the visual evidence. We have to trust our eyes, the morphology, because our ears, the radar just aren't working in this context.
This feels like a classic scientific standoff. The visual data screams, yes, it's a glacier, and the radar says, I have no idea.
And in the complete absence of radar confirmation, the Deception Island analog becomes the absolute strongest argument we have. We know for a fact this exact morphology means buried ice on Earth. It is by far the most logical explanation for what we are seeing on Mars.
So let's assume for a minute that they are right. Let's assume Hecates Tholus is indeed sitting on a massive buried glacier. And let's assume, as the article suggests, that this might be true for other massive volcanoes on Mars. Olympus Mons, Argia Mons, Ascraeus Mons.
It would completely change the inventory of water on Mars. We aren't just talking about a few hitting buckets of frost. We are talking about hundreds of cubic kilometers of pure fresh water sitting near the equator.
So what does this actually mean for us, for the future of human exploration on Mars? Because this really feels like the big so what moment of the whole discussion.
It is a total game changer for what NASA calls in situ resource utilization.
ISRU, living off the land.
Right. Instead of bringing all our water from Earth, which costs roughly $10,000 a bottle just in launch weight, we mine it right there.
So if this theory holds up, we don't need to go to the deadly poles anymore. We don't need to freeze to death in the dark. We can land comfortably at the sunny equator, right next to a volcano, which might even still have some deep residual geothermal heat, and we could just drill.
We drill through a few meters of soft volcanic ash, and bam, we hit pure, ancient, massive ice.
And from that ice, we get water to drink. We crack the hydrogen and oxygen to make literal rocket fuel. We make breathable air. It becomes the ultimate gas station and oasis for a future colony.
It sounds perfect. It honestly sounds too perfect.
It usually is, and this is where the other shoe drops. The legal shoe.
The Outer Space Treaty.
Article 9X of the 1967 Outer Space Treaty, to be exact. It is the foundational document of all space law, and it has a very specific clause about harmful contamination.
This goes right back to what we talked about at the very beginning, planetary protection protocols.
Right. We avoid the poles because they are special regions. We don't want to accidentally introduce our dirty Earth microbes that might kill off native Martian life or completely mess up our science experiment.
But right now, we feel okay about landing rovers at the equator because we assume it's dry, dead rock. No water, no potential for life, no problem.
Exactly. But if we prove that there is massive, easily accessible water just a few meters under the surface of these equatorial volcanoes,
then the equator instantly becomes a special region.
Yes. If Hecates Tholus has water, and if that water is accessible, then technically, under the current COSPAR guidelines, the Committee on Space Research, it becomes a highly restricted zone.
So the exact moment we definitively confirm the resource exists, we might legally ban ourselves from ever using it.
That is the dilemma. It is the ultimate catch-22, the ultimate irony of space exploration. We are spending billions of dollars searching desperately for the one thing we need to survive. But because that thing, water, is also the absolute prerequisite for life, finding it triggers the exact international protocols designed to protect life.
We need the water to stay alive, but if we touch the water, we might be committing a massive crime against science.
Or a crime against potential alien biology. It raises a genuinely massive ethical question. Do we have the right to dig up and exploit these resources to fuel our rockets if there is even a 1% chance that there is dormant microbial life waiting inside that ice?
It's not just an engineering or science problem anymore, it's a fundamental philosophy problem.
It is. And it's one we are absolutely going to have to solve before the first starship lands with humans on board.
So how do we resolve this standoff? How do we find out if the ice is really there without triggering a total legal lockdown or accidentally contaminating the site?
Well, the article points out a harsh reality. We can't do it from orbit anymore. We have hit the absolute limit of what we can see from 200 miles up with our current satellite.
We need boots on the ground.
Or robot treads. We need a dedicated mission to Hecates Tholus. Not just to look at it from above, but to actually touch it, to drill down.
There are some interesting proposals for this, right?
There are concepts being developed. There is the idea of fly radar, which is essentially a drone or an airplane that would fly directly in the Martian atmosphere.
Oh, that solves the geometry problem.
Exactly. If you are flying a drone just 1,000 feet off the ground, you can fly alongside the volcano. You can look directly at the slope, not just down on top of it. You can get that specular reflection. You can definitively confirm the ice without ever having to touch the ground.
But eventually, someone is going to want to actually drill.
Eventually, yes.
Yeah.
And that will be the moment of truth for humanity on Mars.
You know, when we started this discussion, I really thought we were just talking about some weirdly shaped rocks. But this connects absolutely everything. It connects the history of whaling and volcanoes in Antarctica to the ancient volcanoes of Mars. It connects the complex physics of radar scattering to the international ethics of biological contamination.
That is the beauty of comparative planetology. You pull on one weird little thread, a donut-shaped island in the South Shetland chain, and it completely unravels a mystery on a planet 140 million miles away.
It really makes you look at Mars completely differently.
It does. And I want to leave you, our listeners, with that exact thought. We tend to think of Mars as a fossil, a dead thing, just a static red marble spinning in the dark. But if DePablo and his team are right, Mars is much more dynamic than we ever gave it credit for. It is a world that is actively holding on to its past. It is wrapping its precious water in heavy blankets of ash. It is hiding its greatest treasures in geological time capsules, just waiting for someone clever enough and careful enough to actually find them.
And it challenges us. It demands that we be better explorers. We can't just be tourists looking at the scenery from orbit. We have to be detectives, and more importantly, we have to be stewards.
As we plan to become a species that lives on two worlds, we have to grapple with a heavy fact that the second world isn't just a blank canvas for us to paint our bases on. It has its own deep history, its own complex geology, and maybe, just maybe, its own life.
And perhaps, thanks to a fiery little island called Deception, we are one step closer to finally understanding it.
That is a wrap for this deep dive. I highly recommend you go search for Deception Island and look at the photos. It is hauntingly beautiful. And then go look at the orbital images of Hecates Tholus. Once you see the resemblance between the two, you really cannot unsee it.
It's uncanny.
Thanks for listening. Thanks for being curious. And as always,
keep looking up.